Okay, I'd like to thank the organizers for giving me this possibility to talk about this project. I will deal with auxiliary field quantum Monte Carlo. This is a project we have studied in the last few years, and we are investigating the possibility of extracting for fermionic systems dynamical imaginary time correlation functions to give access to dynamical properties, excitation spectrum, response functions, or similar. Our idea has been to study quite deeply the approximations involved in such methodology by comparing its results with exactly solvable models, and to study the relationship between the exact solution and the auxiliary field solution. Okay, first I'd like to introduce a bit the algorithm. Maybe not all of you dealt in the past with auxiliary field. We are dealing with zero temperature quantum Monte Carlo methodologies. As it is well known, the key object is the imaginary time propagator, whose role is twofold. On one end, starting from any well-behaving trial wave function not orthogonal to the ground state, it provides in the limit of big imaginary times the ground state, and from this, as in typical quantum Monte Carlo schemes, one can evaluate energy, structural properties, and general static properties. But on the other end, such operator can be plugged into a correlation function, making it dynamical, and such correlation functions contain information about dynamical properties, excitation spectrum, scattering response function, or even static response function, which can be derived as integrals of such functions. In the auxiliary field techniques, such operator is not dealt with in the configurational space, as in typical Monte Carlo application, but is dealt with in the Hilbert space of the physical systems, relying on an arbitrary basis of one-particle states. Precisely, the starting point is a very general interacting Hamiltonian, which can be written in second quantization formalism, starting from any basis in the one-particle space. A point is that the basis has to be finite, which could be either exact, depending on the model you are studying, or it could be an approximation, and afterwards one can investigate the limit m to infinity. Starting from this formalism, there are a bit of passages one has to do. The first point is writing the Hamiltonian, that can be shown to be always possible, as a sum of a one-body term and the sum of squares of one-body operators. The interaction appears in the square, in the fact that they are squared. Then the typical Trotter decomposition, making small time steps playing an important role, and the primitive approximation that break the exponential into several parts, depending on how we have written the Hamiltonian operator. And the key point is the following, that this operator can be actually written out exactly as an integral over subsidiary variables, typically named auxiliary fields, weighted by a Gaussian multidimensional measure. The actual dimensionality depends on the problem, on the Hamiltonian, and an operator depending on the auxiliary field, which has the form of a propagator, namely of a non-Hermitian propagator in general, in which such one-body operators appears linearly and are coupled to those auxiliary fields introduced. So it is possible to rewrite an interacting propagator in terms of independent particles propagators characterized by stochastic fluctuating fields. The fee one has to pay is this integration, which recovered the full interacting Hamiltonian. The fact that we have introduced a one-body propagator make the one fermion formulas, the independent particle formulas, very important in this context. Namely, single particle independent particle states as later determinants, very general, built with single particle orbitals. They actually form a very big manifold in the Hilbert space of the system and can also easily be stored in the memory of a computer or anything, considering the projection of the orbitals on the one particle base one has chosen in the very beginning of the problem. The usefulness of this formula lies in the fact that the operator G of theta, which is the one-body propagator introduced before, actually transforms a Slater determinant into another Slater determinant, which is not true for the general interacting propagator, which, if when applied to a Slater determinant, actually takes it in a point in the Hilbert space, which is no more a Slater determinant. But for a single auxiliary field, representation, phi is mapped to phi prime, and in terms of the associated matrices, the relations is quite simple. In the next slide, I will write it down explicitly. Of course, the integration over the auxiliary field finally take out of the set of the Slater determinants. The transformation of the matrices, which is just the dynamical ingredient of the algorithm, is immediately written from the definition of the operator G of theta. Any of these single particle operators as a matrix representation in the one body space. And if one takes the matrix exponential of the appearing matrices, one has the transformation of the associated matrices. This actually is a non-trivial result. This proof requires a bit of algebra, but it can be shown. And it is a key point of the algorithm. Well, in this way, if one considers a trial wave functions, which is itself a Slater determinant, for example, the NR3 Fock solution or orbitals coming from the FT calculations, one can stochastically sample the Gaussian auxiliary field that generates a movement in the manifold of Slater determinant, and waiting for a sufficiently long imaginary time, one recovers the ground state of the system as an integration weighted by a standard normal Gaussian measure of Slater determinant. And this I write in the following way: the ground state as an averages of Slater determinant over auxiliary field, over the stochastic auxiliary field paths. Namely, the average of Slater determinant is not necessarily a Slater determinant, and in general it is not. But the single realization of the random variable are themselves Slater determinant. From this expression of the ground state as an averages, one can use the law of large numbers to estimate the ground state as an average over Slater determinants. And this is itself an algorithm to sample the ground state, because one is simply to sample uniformly distributed and Gaussian, the simplest possible case about Gaussian random variables, and one has the ground state. Well, actually, a big deal of uncertainties arise if one uses this plain version of the algorithm. Shiwei Zhang invented a way to, this is just one of the articles speaking about this, to improve the motion in the set of Slater determinants to reduce the variance of the calculations. His first point is that it shifts the auxiliary field so that at each time the auxiliary field is not completely independent of the past, but it starts from a configuration. It's like a drift. Many possible choices of this function can be constructed. Shiwei typically uses this form, which is chosen to minimize fluctuations in the weight of the determinants, as I will show in a minute. And the other point is that to each determinant, a weight is associated, and the dynamic of the weight becomes an expression which closely reminds the typical expression in Monte Carlo, in which a local energy appears associated to one's later determinant, and such local energy is the real part of the matrix element of the Hamiltonian between the trial wave function and the actual determinant in this position. This is an approximation, and namely the strongest approximation in the algorithm, because in principle this could be complex, and this introduces a phase problem in the method. And moreover, to write this expression, one has forgotten another part, which is auxiliary field dependent and actually fluctuating around 0, but fluctuating. This factor, which has been introduced by Shiwei Zhang, is another control that is meant to avoid zeros in this complex plane, because there is some parallelism between the zeros in typical configurational quantum Monte Carlo and the zeros in this plane defined by the overlap with the trial wave function. If this happens to be zeros, several problems enter the algorithm. But the combined effect of the real local energy approximation, this phase control which prevents the phase to flips too rapidly, that is connected to being near the zeros in the complex place, provide a representation just like the one before, but some weights appear, and the determinant are divided by this overlap. And this, of course, has not to be 0, otherwise this expression is not well defined. But from this expression, one can evaluate averages over the ground states. Actually, we have verified empirically that zeros are avoided. Consider this is 26 electrons in the Gellium model, an application of the algorithm. And what this important sampling shifted random walk do is to create such a void near the 0. This is the complex plane defined by the trial. If you start from, for example, the Hartree-Fock solution, which could be somewhere here, and overlap maybe could be real, then you have a dynamics that bring in equilibration time bring your determinants in such a region, and then the effect of the drift and on the important sampling keep, in general, the walkers out of the zeros of such a complex plane. Naturally, the size of this hole decreases exponentially with the number of particles. If you see the scale, this actually is what happens. And from this expression, from the formalism I have presented, one could, of course, evaluate directly the ground state. I will come back to this point in a minute. But the average of observables can be readily computed. In the simplest case, for observables commuting the Hamiltonian, inserting the stochastic linear combination providing a ground state, one has this simple expression. And when one knows the matrix associated with this determinant containing just the overlap of the orbitals with the basis set, this is a simple expression. It converts some matrix, some linear algebra operators. Knowing the operator, no difficulty in this. The evaluation of pure estimates is a bit more complicated, since an exponential of the Hamiltonian has to be have to be plugged here to act on the bra in this expression. If one writes this in terms of auxiliary field, the operators G of eta cannot bridge across A, so they have to be applied on the left side as their dagger. And this introduces a new way where is again an average, but the matrix elements do not contain the C trial, but another later determinant, which is readily constructed, starting from C trial, known as a random walk, arriving to a given determinant. Then such S operator, if S is the number of side steps, should be evaluated here, but one has to keep track of the product of matrices, take the dagger, apply the C trials, and this give back. Of course, this introduces a bit of noise, because one should be sure that this time is long enough. One has a product of matrices, and this can fluctuate, can have quite big fluctuations. I will show then afterwards some results, some empirical results about that. What about imaginary time correlation functions? Few attempts have been made in literature. I have followed an idea which appeared in this article by Feldbacher and Assad, in which a scheme has been proposed to evaluate imaginary time correlation functions. It's not trivial at all, because this operator is lies between the two operators, and some operators G in its STRATONOVICH representation remain trapped. And this is not trivial, because here one has a random walk, which starting from psi trial try to reach psi 0, but then an operator acts, and an operator, even a very simple operator, one body, for example, density fluctuation, when act on a Slater determinant, does not give a Slater determinant, and this breaks down the algorithm. Assad proposed a way of commuting the operators inside this propagator with what appears here. Precisely, it suggests to use formulas like this. That's if you take tau equals to n times steps, you have n operators G. Then they reach an operator which could be simpler to construct a green function, but we would like to do density response function. One has two operators, one creation and one destruction. And this can be worked out. It's not so difficult that this product of operators can jump over. But the fee to be paid is that a product of matrices, which contains only the matrix applied to the operator in the propagator, have to be reminded during the simulation. The result is a bit intricate, but not so difficult. The formula looks very strange, but the fact is that if one wishes to evaluate the imaginary time correlation function for n time steps, one has to consider segments of the random walks of length n, and on this n one has to memorize to remember the product of such matrices, also the inverse. One is related to the creation and one is related to the destruction operator. And what remains is quite typical. One has a weighted averages with a shift in the time that has to be accounted for. One has a matrix element, which could be a quartic one, that has to be treated with the Wick theorem, but this can in principle be implemented in the algorithm. It's a bit of matrix algebra, but no more. And of course here I've put also the back propagation to make the estimate a pure estimate. Okay, Now I pass to the test of such algorithm. In principle, it can always be written. Once one has chosen a single particle basis, then the machinery can start. We have chosen the Gelium model in 2 dimensions as a test system. The Hamiltonian operator in k-space representation, choosing as one particle basis simply plane waves and spin eigenfunctions in a given direction, is the following. One has a kinetic term. This is a constant arising from the periodic boundary condition, that's typical. And this is an interaction with a Coulomb potential, which is in 2 dimensions, is regularized in the origins by the background of positive charges, and is 2 pi divided by modulus of the wave vectors in the other points. To implement the auxiliary field scheme, one have to insulate a one-body part, which simply appears a k-dependent constant, so nothing complicated here. There is the constant, which does not affect the algorithm. And here are the operators which are squared. The operators are one-body operator, namely non-Hermitian one-body operator, not here any path, involving density fluctuation in the system. The necessity to use a finite basis requires to select a finite region of kappa space. This BK is just a cutoff in kinetic energy that results also in a cutoff about transferred wave vectors. There only vectors connected blue points can appear in this operator. What we would like to compute for this model is energy structure, and also try to evaluate imaginary time correlation functions of the local density operator. Well, since many approximations are involved, there could be size effects, finite basis effects, many things. We have followed the idea of simplify the situation in order to stress the most important approximation inherent to the method. And then we take the same Hamiltonian, I write it before, for a very few electrons, namely 2 electrons, and we fix the cutoff in kinetic energy. And if we consider 2 electrons and not so many basis sets, this Hamiltonian can be solved exactly via numerical diagonalization. This is the first example. This is a case in which we have only 2 electrons, one spin up and one spin down. Here Rs, the size radius is 1. And this is the exact solution for 13 plane waves. If one considers a cutoff in energy, 13 plane waves, this is the exact solution. The similar means that there are more digits here. So this is a pictorial representation, but this means that the true ground state of the simple toy model contains, this is the Hartree-Fock solution, and conserving the momentum, any possibility of displacing the Slater determinants, the decay of the wave vectors of any electrons. And we can compare this state with the one sampled with auxiliary field methods. And this is the result. Here I've simply labeled the states in the 2-body Hilbert space. The number is arbitrary, but one has just to fix. And what we find, the green ones are the exact components of the ground state on the elements of the basis in the 2-particle space. The red one is the result of the auxiliary field. Naturally, it is a random walk, so some noise always exists. But the very interesting point is that the algorithm actually captures all the excited states. There are more than 3 Here I've represented just 3 because you have to consider exchange between the direction of the spin. But every state is recovered, and the discrepancies are of the order of magnitude of the noise in the random walk.
But here you use constraint path approximation or not? I mean, it's exact, just
No. All the approximations I introduced before have been used here.
So with
but
constraint path you get the exact result, but you will have sign problem.
Shiwei says that the sign problems, meaning an explosion of the variance, does not manifest itself with the constraint path.
Yes.
Without you would have a...
Without, yes, but here is with the...
which there is no sign problem, you don't need the constraint, right?
Yes, you're right.
Whether with 2 electrons you have sign problem at all.
This is a problem without sign problem. Up, down, you have no sign problem. For example, this is an example where some sign problem could manifest. Here we have 2 spin-up electrons. In fact, here the ground state is degenerate because it depends on the symmetry. If you choose this Q vector, you have another ground state. This, if you choose this one, these are the components of the ground state with this symmetry. And again, in this situation, the algorithm, with a bit larger noise, find out the single particle states in a quite precise manner.
What is the normalization here? Because
it's normalized to 1.
Both.
Both,
Green
yes.
and the red.
Yes. What? Yes, I hope so. I have to check again.
If I do, I mean, just at first sight,
I have a cut here because great part of the normalization is about yes, yes.
Okay.
So you recover the normalization.
So it's
See, yes.
some kind of.
It looks contradictory, but here is a big a big part of the normalization. These are other properties. These are the total energy for the up-down system, RF1. You have always equilibration, an equilibration time, and then you arrive. The no sign problem. But here, this is a quite trivial. But this situation happens also for more than 2 electrons, and also Shiwei represent. The green is the exact result.
So you are below the exact.
We are a bit below. There are no claim of being variational methods. Also in the work of Shiwei, Zhang insists. And also there is this typical effect that before reaching a stable state, quite always the energy shows a minimum. I've been discussed with Shiwei Zhang about this. Interpret this as a non-variationality of the algorithm. This is another example. This is a pure estimation of the kinetic energy. Here, some noise appears because you have to multiply some matrices to obtain this result. And these are the imaginary time correlation functions for this very, very simple system with very, very small plane waves basis. The result is very interesting.
So we have also the exact here.
The green is exact, yes. I'm sorry, but maybe it's not so visible. I have to maybe. This is increasing the number of plane waves, and this start to be a difficulty, quite unavoidable, because this is a sign problem in this situation. Because to obtain the FQT with just 49 plane waves, you have to multiply a number of matrices and to take the inverse. And the number of matrices is this number times the time step you have
You talked about the inversion of this curves too?
The inversion?
The inversion.
The Laplace inverse transform? Yes, we've tried. Then I will show when we discuss in the afternoon. I'll show you some results.
Excuse me, sorry. Is the thickness of the red line
the error bars?
Are those the error bars?
The error bars of the calculations, yes. But this appearance, it's very, very difficult to stabilize this because you have to multiply many matrices and to take the inverse. And when you will regularize the matrix, the inverse does not obey. This is a difficulty. Assad claims that it is possible for the dynamical green function to factorize the calculation. That is to evaluate long time values in terms of shorter time estimation. But for these functions and for our form of the algorithm, I wasn't able to reproduce his formulas. Maybe it could be a topic.
Because I thought it was a solved problem.
Yeah?
Yeah, so have you tried singular value decomposition and things like that to stabilize this?
We have done many things. We have divided the matrices by many, the trace, the norm, the determinant.
That's known to be not enough. Yeah.
The singular value decomposition we have tried, but it was often very noisy. Yes.
Yeah, I was just going to ask that. So that increasing error that you find there, is that due to? Oops, I had a bad effect. No, I was just asking that. Is that due to the round-off error, due to the fact that you have sort of too many time slices that you have to?
Too many matrices to be multiplied. Yes, it's due.
So it's not the sign problem.
Yes, it's a numerical stability problem, which is not trivial to solve.
Yeah, it sort of diverges exponentially like that.
It could be very interesting to discuss possibilities of stabilizing.
Basically, I mean, the problem was solved by orthogonalization. You have to do a more sophisticated.
Yes, we are thinking about also Lanczos multiplication method.
This has been solved. I don't know what you can do.
This is a comparison with a path integral ground state technique, which for such
pigs, I have to remember.
pigs, which for this system is exact because no sign difficulty here. One up, one down. You have a bosonic system, and the agreement is quite close. Of course, the pigs cannot use a finite basis set. It has to consider infinity basis, and it's interesting that we reproduce Peake's results.
Well, the agreements here might be a little misleading, of course.
Yes, the
because
Peake's
of
one
plus
have
four,
the.
I mean everything. I mean.
Yes,
great,
you can
more
do.
or less. So
We have to do long simulation to restrict the error bars.
no, but besides state, I mean, it's the signal that is buried into that transform
Yes.
that actually depends very on the details.
Yes, I know.
Oh wait, but this tau is imaginary or is real?
This tau is
It's
imaginary.
but you can invert the.
But this is not already inverting.
No, it's not. But that's why what I'm saying.
Okay.
I mean, when you
Inversion-
invert, the tiny differences. I mean,
That's of course. Yeah.
So the comparison like that makes things look better.
Yes. yes, of course.
No, but the point is that if you use other nodal restrictions, such as fixed node, you would see a big difference even at this level.
Okay, that's an interesting point. Yes, because this means that it's even worse when you transform.
This is a way which doesn't have the same problem and has a better accuracy than.
Yes,
I thought fixed node was wrong.
Yeah, you can.
Exactly.
Yeah,
So
it's
that's-
not a misleading.
In the future, we will able to to give also comparison with about problems in which fixed node is active. Here, the Peake's simulation is exact in principle. This is a case. We have obtained increasing the size radius. RS equal 2 is again quite good. Of course, one have to run long simulations to decrease the error bars. When RS becomes 3, some problems begin to occur. You need longer and longer simulation to stabilize the profile of the curves, and the numerical stabilization problem become more and more severe at big RS.
I was just wondering, about the error bars. They are obviously not statistical error bars because they sort of overlap, right?
So you see that these are not well estimated. Yes, you're right.
Correlated, so
These are correlated.
Okay, all right.
because it's done with a single. But it's confusing because you say this error bar may be due to the numerical accuracy. So it's some kind of the
Yes.
So not
At,
error bar, you should say
No, of course, because there is
Like a band or something.
some scat.
there is the real local energy approximation, which is an approximation. It could bias systematically the result. And the green one is an exact. Starting from the Hamiltonian, this is the exact FQT one would like to.
You're saying there is a numerical stability problem. For small tau, the error bar I have to believe. No?
And numerical stability problems can take place at long tau. But maybe for this tau, no numerical. This could be an effect of the approximations, not on the stability of the multiplication of matrices.
Here the error bar is what, factor of 2 larger than
Yeah, it's
I mean it's so it's
So it seems to be consistent here. But in the previous plot, I always add the error bar.
Yes,
This is
yeah.
bad, but it's numerical stability.
Yes, this one.
That's
This one. This is
that's completely
Unless,
Yeah.
yeah.
this is another effect.
In that case, I would trust
Yeah.
the error bar. No? Why should-
Maybe here we have to run longer and longer simulation to stabilize the error bars. This is a possibility. There is also the possibility that the approximations start to become visible. It's a possibility. This is the up-up system, and again this instability problems is evident already at 49 plane waves, and this could be a difficulty when extending the size of the system. You have many particles, many basis elements. It could become a bit difficult. Here is with RS equal to 2. It's not disappeared. It's appears somewhere here, the instability problem. And I end this discussion presenting some results for more electrons. Always the Gellium model. We take more or less 200 of plane waves basis. I won't discuss it now because it requires the inversion. If you want, we can discuss in the afternoon or whenever you want. And here we have only preliminary results because we would like to end the discussion of exactly solvable models, so to have everything under control. But here there are some results about these are about static properties computed with the auxiliary field method. Here is a comparison between our result and the result appearing in literature about the electron gas. We have computed the static structure factor.
Excuse me, sorry about that. So the S of Q here, is this an integral of S of Q omega?
No.
Okay.
No, not. This is a static property.
Okay.
The static. It's not the key Q. The key of Q. This is
Omega
one.
equals 0 or static?
This is static. Yes.
And
This
the
is the-
transform of the percolation function.
yes.
Yes.
And so what you need dynamics?
No, this is not dynamic. This is a static properties which requires the backpropagation technique to deal with pure estimates, but not. We are studying the density response function, which is the integral of SQ omega divided by omega, and this could be a response function, but we we are studying it, we are also trying to extrapolate the thermodynamic limit of such quantity. This is another static simple quantity, which is the occupation number in K space. Also compared with the Sepperly results, it's quite it's very compatible. And that's all about auxiliary field quantum Monte Carlo. The idea is to proceed now about these tests. The evidence is that small system can be quite accurately studied by this method, and this method is also very flexible, since one can easily change the one particle basis to choose something which suits the problem one is studying. And if one would like to recover dynamical properties, one has to keep into account that multiplying large matrices, instabilities can grow up quite readily, and this is a matter of fact. So I can conclude here. If you want to discuss in the next days or in the afternoon, I have also I can discuss also about inversions, about what can be extracted from imaginary time correlation functions. If you have questions.
Okay, thank you. More questions? Comments?
I have a question about this. You showed the overlap with the, what is avoiding of the zero region in the overlap test.
See? Yes?
And you showed a circle of very small numbers.
Yes?
But then in the comparison with the exact wave function, the component under the Fock solution was close to 1.
Yes?
So
But this comparison was about the 26 electrons problems, not about the 2 electron problem. In the 26 situation, all the overlaps goes down as the exponential of minus n, so something more complicated can happen.
but still this would not be a ring because
It starts from, maybe it's a ring. We can check. I have all the results about this ring in the simple cases.
I have a question. So you're using auxiliary field quantum Monte Carlo.
Yes.
One comparison that I might be interested in is, what if you took the regular quantum Monte Carlo with the sign problem? Okay.
The regular configuration of quantum.
Absolutely. And did the calculation of the imaginary time correlation with the exponentially decay function with larger and larger error bars with the same amount of severe
This is
time.
very interesting.
How would you, how much better is this compared to what
Yes.
you get?
We are organizing all our codes and our resources to make such calculations, to compare with fixed node, with full sign problem, quantum Monte Carlo. Yes. Readily we will have such results.
So you want to keep the sign both in the configuration space and the determinantal space and see which is the.
Yeah.
So let me understand that, because you mainly have used exactly the same algorithm as Assad has proposed.
No, not
yeah.
exactly, because Assad proposed the strategy of commutating the operator and I've used this idea. But Assad used them for the green dynamical, the green function in Imagine, the Matsubara green function. On one hand, he has just one operator to be to commute
because
with
he's
the
able
operator.
to do imaginary time up to 20 or 1.
Yes, but he claimed that he explored a situation where no sign problem is. In his article, you find this. He used a Bose-Hubbard model.
The numerical stability problem is the same name.
But if he used some tricks, he factorized the evaluation of the dynamical green function. He built up a formula, yes, but in this formalism I wasn't able to reproduce the formulas. That's, I think
Yeah,
that
that's
in
not
this
written very well.
in this
You have to send a message to it.
yes, but also
And you have to ask. But
it does
I'm
not
sure
use
works.
it does not use precisely the Shewenzhang implementation. There is a problem with the later determinants appearing. He commutes things that, in my opinion, cannot be
I discussed
commuted.
with him. You have to discuss with him.
Okay.
I do not understand.
I wrote also the PhD thesis. I read also the PhD thesis of Feldbacher, rating with Assad. But also there, the formal is a bit, for me, it's a bit difficult to understand and to reproduce. Of course, this could be a very important thing.
You should solve this very.
It could be very important because at the small tau we have beautiful results.
Done? Okay. Thank you again.
You're welcome.
Thank you very much.
But